Hind everyone. This is Jyoti Sharma once again presenting you the topic of electrical machines, which is unit 4 of the subject basic electrical engineering, having the subject code of KEE 101 according to AKTU. Okay, so in the previous lectures of ours, which is related to electrical machines, we have seen various DC machines. We have discussed their construction, their working principle, their classifications, their utilizations. We have also discussed a 3-phase induction motor, right? How does it, what is its working principle, what is rotating magnetic field, right? Continuing with the topic, right? We have discussed the classification for 3-phase induction motor, likewise the squirrel cage induction motor and wound rotor. What are their applications, what are their differences, right? Now, we also need to know that what is the torque being produced by a 3-phase induction motor and how does it varies according to the slip or according to the speed, okay. So, going for the torque equation, we have earlier seen in case of 3-phase induction motor how the variation in the slip or how does the slip makes the variation in the rotor frequency as well as with the various parameters of the rotor circuit of the 3-phase induction motor. So, today's topic would be the torque equation and torque slip characteristics. Then we will be continuing in with the single phase induction motor, its construction, what is this double revolving field theory is all about, and what are the types of single phase induction motor. Okay, now coming to the torque equation. Now, the torque of a 3-phase induction motor, that depends upon the 3 factors. One is the rotor current, the power factor of the rotor circuit and the flux which links with the rotor. What is that? That is phi, right? So, the torque is basically proportional to phi I2 cos phi 2. Phi is the flux which links with the rotor, I2 is the rotor current and cos phi 2 is the power factor of the rotor circuit. In fact, these are all under running condition. Once again, this flux what we are discussing, this is once again the same, the part of rotating magnetic field which is reacting with the rotor, that is nothing but phi. That phi is proportional to the supply, the induced EMF in the stator circuit. That is what we are calling it as E1, right? Also now this E2, E1 is proportional to E2, E1 is some K times of E2, right? So, obviously that is proportional to E2 as well. So, I may even substitute phi as E2, right? Then the another parameter I have substituted phi as E2, okay. Then I2R, that is the rotor current at running condition. How do we give it? We have already given the expressions for that. That is given by E2R by Z2R. E2R is being given as S times of E2 and Z2R is given by under root of R2 square plus Sx2 whole square, right? Similarly, the power factor of the rotor circuit cos phi 2R, that will be given by R2 by Z2R, because R2 doesn't vary with the frequency, that's why it used to remain constant. That's why that is R2 upon Z2R, once again substituting. So, now I am having all the 3 values, flux proportional to E2, I2R is equals to this expression and cos phi 2R equals to this expression. So, just substituting that in the expression of torque being proportional to phi I2R cos phi 2R, I will be having the expression of torque that is just proportional to substituting. It is proportional to S times E2 square R2 divided by R2 square plus Sx2 whole square. Replacing this proportionality constant with a constant 3 upon 2 pi ns, where this ns is nothing but the synchronous speed 120 f by p, but in rps, revolutions per second, right? So, this gives us the torque equation for a 3-phase induction motor. Now, what should be the expression for the torque for a 3-phase induction motor under running condition? We have already derived that. So, what will be the starting torque for it? We know that at the very starting of a 3-phase induction motor, the slip, the value of the slip, that used to be 1, right? So, just substituting our actual expression, that used to be K times SE2 square R2 divided by R2 square plus SX2 whole square. Just substituting here, S is equals to 1. We'll be having the above expression. So, the starting torque is given by K times E2 square R2 by R2 square plus X2 whole square, right? The thing to be considered over here is, the thing to be seen over here is that the starting torque is directly proportional to the rotor resistance. So, as we keep on increasing the rotor resistance, which is possible in case of wound rotor motor or slip ring induction motor. In case of squirrel cage, this provision is not there because the rotor circuit is completely short circuited with the help of end ring. So, we can't introduce any extra rotor resistance in it. We have discussed that in the earlier lecture. So, if we are able to increase the rotor resistance, likewise in case of the squirrel cage, in case of wound rotor induction motor, in that case, the starting torque can be increased, right? Now, what is the condition to have the maximum torque in a three-phase induction motor? Now, in the torque equation, we have seen that the torque depends upon the slip at which the motor is running, right? The supply voltage to the motor is usually rated and is constant. So, there exists a fixed relation between E1 and E2, as E2 is also constant, right? Similarly, R2, X2 and NS, these are also constant for an induction motor once being constructed. So, mathematically, for a maximum torque, what we have to do? I can even say that because the torque is directly now, it is just depending upon the slip. So, according to the law of maxima, if at all I want to have that condition, so I'll be differentiating the expression for the torque with respect to slip and equating it to 0, right? So, the expression for the torque is K times S E2 square R2 divided by E2 square plus SX2 whole square, and just differentiate it with respect to slip, right, and equating it to 0, we'll be having the expression S square is equals to R2 square plus divided by X2 square, right. Obviously, neglecting the negative slip, the positive value of the slip has to be R2 upon X2. So, this is the slip at which the torque is going to be maximum and is denoted as SM, right. So, once we just substitute the expression over here, the condition what we have gone for the maximum torque is this, the torque would be maximum for a three-phase induction motor when the value of the slip is given by the ratio of the rotor resistance to the rotor reactance, right. Now, if at all, that is the condition, right? But what will be the magnitude of this maximum torque what we are going to attain, right? So, just substituting the value of that maximum, the slip corresponding to the maximum torque in the actual expression. So, I'll be just, this is the expression what we used to have, right? Just substituting S is equals to Sm. I'll be having K times Sm E2 square R2 divided by R2 square plus Sm X2 whole square, right? And Sm is equals to R2 by X2. Substituting Sm as R2 by X2 in numerator and denominator in both. So, the expression for the maximum torque would be given by K times E2 square by 2X2, right. Now, once again, the thing to be noticed over here is, that in case of maximum torque, this expression is entirely independent of the rotor resistance, right. So, the maximum torque is independent of rotor resistance. As we have seen in the starting torque, as we keep on increasing the rotor resistance, the starting torque will increase. But the maximum torque is not going to get increased with the increase in the rotor resistance. But definitely the slip at which this maximum torque is achieved, right, that slip will vary according to the rotor resistance. That Sm is equals to R2 by X2. That is directly proportional, right. So, these are certain observations what we have got from the expression for the maximum torque, that it is inversely proportional to the rotor reactance. It is directly proportional to the square of the rotor induced EMF at standstill. It is just E2. It is not E2R. And the most interesting observation which I just explained is that the maximum torque is not dependent on the rotor resistance, right? Okay, now very quickly coming to the torque slip characteristics of a three-phase induction motor, right? So on this we have taken slip on the x-axis and the torque on the y-axis, right? We can always place the speed also over here, right? I know that the speed is going to be 0 where the slip is equals to 1, right? When slip, if at all I say is 0, then obviously n is equals to ns, right? And this is the maximum torque, what it can be seen. So obviously this has to be some Sm. This is the slip. This is the slip corresponding to the maximum torque and is given by R2 by X2, right? So it can be seen now, this is the characteristics for a three-phase induction motor. It can be divided into two portions, right? One is the portion in which the slip is towards 0, that is between 0 and the slip corresponding to the maximum torque, and is the region, and another is the region which is between the slip is equals to 1 to the slip corresponding to the maximum torque, right? So this I must be saying is the high slip region and this is the low slip region, right? So now it can be seen that in the low slip region, the torque is directly proportional to the slip. As the slip is increasing, the torque is also increasing. It is directly proportional and that can be very well understood, right? What is the expression for the torque? What we have got for a running condition, that is K times S E2 square R2 divided by R2 square plus SX2 whole square, right? And for the lower slip region, what is happening? The slip is very less, right? So the value of slip is almost equal to 0 and it is very less. In that case, this whole term would be very much smaller compared to R2 square. So I may neglect that, right? If this is being neglected, so it can be directly seen. Rest of the things are all constant, right? E2 is also constant, R2 is also constant, right? K is also a constant. So I'll be directly getting that the torque is directly proportional to slip, right? Whereas in case of higher slip region, it can be seen that, right here, the torque high slip region. In this case, the torque is inversely proportional to S, right? It is inversely proportional. In this case, what is happening now? Now, once again, the torque is given by K times S E2 square R2 divided by R2 square plus SX2 whole square. That's correct. But this time, the slip is not equals to 0. It is not tending towards 0, right? It is tending towards 1. So it is having a value, a finite value. In this case, the rotor resistance square, this is going to be very much negligible compared to this. Once again, rest of the things likewise E2, R2, X2, these are all constant. S is also, K is also constant. So I'll be getting T is proportional to S upon S square, right? And I must be saying T is inversely proportional to slip, or the torque is inversely proportional to slip. So that's why we are getting these kinds of graph. Fine. Now, coming to one more important thing, right? We have called this region as low slip region, and this low slip region is also being called as stable region. Stable region, right? And this high slip region, this is also being called as unstable region, for the reason very well understood. It can be very much easily understood. What is that? Okay, so let's continue with the high slip region. So what we have seen in the high slip region is that the torque would be inversely proportional to the slip. Okay, fine. Now, if at all I say, if the motor is operating in the high slip region, right, the operating point of the induction motor is somewhere in the unstable region or in the high slip region. At that instant, what is going to happen, right? And now, if we are varying the load, right? If at all I increase the load, if the load is being increased, obviously, what is going to happen with the speed? When the load is increased, the speed of the motor is going to get decreased, right? If the motor speed is decreasing, what is going to happen with the slip? Obviously, the difference will increase between NS and NR. So, the slip is going to get increased, right? The slip will increase. But in this unstable region, what can be seen that with the increase in the slip, the torque is decreasing. The torque is inversely proportional to the slip. So, once the slip is increased, the torque is decreasing, right? But what is demanded by the motor? If the load is increasing, then obviously the motor has to produce extra torque to meet up with the new load demand, which is in higher demand, right? That has to be met with the motor. But the motor is not producing an extra torque. It is in fact decreasing its torque what it is producing. So, what is going to happen? The motor will feel even more loaded, right? The torque which is required by it is not being produced further. Instead, it has been reduced, right? So, the motor will feel even more loaded. So, what is going to happen? If it is, the load is further increased, the speed is further increased, the slip will be further increased, and once again, because of the nature, once again, with the increase in the slip, the torque is once again going to be lesser. And this process is continuing on. It's a cumulative process. So, what is going to happen? Ultimately, the torque produced by the motor is going to be zero, or the motor will come to rest or at standstill condition, right? That's why this complete region, the high slip region, this is being called as unstable region. So, the motor will never be made to operate at the slip which is higher than the slip corresponding to the maximum torque, right? So, always the slip which is in between 0 to the slip corresponding to the maximum torque would be the operating slip, right? Once again, this can be seen very much easily with the stable region, right? In the stable region, once again, when the load is increased, obviously, the speed is going to get decreased, and obviously, the slip is going to get increased. NS minus NR, right? Now, with the increase in the slip, in case of the stable region, the nature is the torque is directly proportional to the slip, right? So, in this case, the torque is not going to get decreased, but the motor is going to produce the extra torque which is required by the new load demand, right? Once that demand is being met, once again, the motor, the speed which is decreasing, that will stop over there, and motor will continuously be running at that particular speed, right? So, that's why this region is being called as stable, and the high slip region, that is being called as unstable region. Now, the very applications of the three-phase induction motor, it is widely being used in most of the industrial applications like industrial fans, pumps, cranes, hoists, elevators, electric tractions also. It is having a very wide range of applications, right? Okay, now, continuing on, but instead of three-phase, we have seen all the kinds of three-phase induction motors, cover all their differences also. Now, coming to single-phase induction motor, we use the single-phase power system more widely than the three-phase system for a domestic purpose, commercial purpose also, and to some extent in industrial uses also, right? So, because the single-phase system is more economical than a three-phase system, and the power requirement in most of the houses, shops, offices, and, in most of the residential areas, that can be easily met by a single-phase system, right? So, the single-phase motors, these are also simple in construction. They are cheaper, in cost. They are much more reliable. They require less maintenance, easy to repair. So, due to all these advantages, the single-phase motors, they find their applications, in the household things, which used to work in for a single-phase supply, likewise vacuum cleaner, fans, washing machines, centrifugal pumps, the blowers, the washing machines, etc. Okay, now what is its construction is all about, right? How does it look like, right? It is very much similar to a three-phase with a slight difference. Obviously, it's a so like any other electrical motor, a asynchronous motor also have two main parts: rotor, stator. The stator of the single-phase induction motor has laminated stampings to reduce the eddy current losses on its periphery, obviously. The slots are provided on its stampings, right, of the stator or of the main winding. The stampings are made up of silicon steel to reduce the hysteresis losses, right. So, when we apply a single phase AC to the stator winding, that is the difference. In case of three-phase, we used to provide three-phase AC supply. It is a single-phase induction motor. We are going to supply a single-phase AC supply. When the magnetic field gets produced, it is, and the motor rotates at a speed slightly lesser than the synchronous speed, which we call it as NS, right. Just to go on with the working, I may say this, but in the later cases, we'll be seeing, does this single-phase induction motor start so easily, right? We'll be seeing that, okay. Going for the construction, the motor shaft, these are the stator, the frame, this is the rotor, the steel part, these are the end shields, right. Coming to the rotor, once again, the construction of the rotor of the single-phase induction motor is similar to a squirrel cage three-phase induction motor. The rotor is cylindrical and has slots all over its periphery. The slots are not made parallel to each other, but they are little bit twisted, a little bit squeeing is being done to prevent the magnetic locking. We have seen that, right. So, the squirrel cage rotor that consists of the aluminium bars or the copper bars, right, or the brass bar, right, and are called the rotor conductors that are placed in the periphery of the rotor. The copper or the aluminium rings, these are being provided permanently to short these rotor conductors, and these are being called as end rings. This is the construction what we have in fact studied in case of squirrel cage three-phase induction motor, right. To provide the mechanical strength, these rotor conductors are being braced, and hence they formed a complete closed circuit resembling to the cage, right. That's why we used to call it as squirrel cage induction motor. The end rings are permanently short circuited. So, the rotor electrical resistance is very small and it is not possible to provide any external resistance as the bars are permanently shorted. So, the absence of the slip rings and brushes that makes the construction of the single phase induction motor very simple and robust. Likewise, in case of three-phase induction motor, we used to have slip ring induction motor. Here, we don't have such kind of construction in case of single phase, right? And it is better also for the maintenance purpose. Now, what is this double revolving field theory, right? So, exactly, we'll first go with what is this double revolving field theory, and from here itself, we'll be deriving actually why we are studying this and what is its significance, Now, according to this theory, any alternating quantity can be resolved into two rotating components, which rotate in opposite direction, each having the magnitude as half of the maximum magnitude of the alternating quantity, right. In case of single phase induction motors, the stator winding produces an alternating magnetic field having the maximum magnitude of 5 Nm, okay, that can be seen. Now, in this case, if at all I say, this is the stator flux. This is the stator flux having the maximum value of 5 Nm. Now, according to double revolving field theory, this alternating flux can be resolved into two rotating flux which are rotating in opposite directions and having the magnitudes, equal magnitudes of half of the maximum, right. So, I am resolving them into two components. One is phi f, that means the flux which is moving in anti-clockwise direction, I am calling it as forward flux, and the flux phi b, that is, this is the flux which is moving in clockwise direction, I am calling that as backward flux, right. And both of these are having the magnitudes of half of its maximum, 5 Nm by 2, right. So, what it can be seen is, both of these fluxes are rotating with a speed of ns. giving an interpretation of rotating magnetic field. So what is going to happen? If at all I just consider phi f, it is rotating at a speed of ns, right, in anti-clockwise direction. Now what is going to happen? The rotor conductors, what I'm having, these rotor conductors are going to experience the flux cut because those are stationary. Exactly that was of three-phase induction motor, right? So the rotor conductors are stationary. I'm having a rotating magnetic field which is moving in anti-clockwise direction. So the rotor conductors are going to experience the flux cut. They are going to have an EMF induced as the rotor circuit is short circuited. So there will be a current. Now a current carrying conductor, that will be experiencing a torque. Fine. So the torque once again would be in such a direction so as to reduce the relative motion. So the motor will produce a torque in the same direction as that of the rotating magnetic field for forward direction. That means anti-clockwise direction, right? It will try to attain the speed of ns, right? And the torque will be produced in anti-clockwise direction. While at the same time, it can be seen the phi b is not going to sit quiet. That is also having its speed of ns, right? It will also try to rotate. I mean, this is the synchronous speed of the field which is being rotating in clockwise direction. So because of this magnetic field also, once again the rotor conductors will be experiencing an EMF, the current, and thereby the torque. So this field is also going to get me a torque being produced, but this time in the backward direction, which is given by the clockwise direction, right? So what is going to happen at the very starting, if at all I see, at the very starting, when both the fluxes are equal and opposite, then the torque being produced by these two fluxes or the fields, that means phi f and phi b, both of these fluxes would be opposite and equal in nature. That's why at the very starting position, the motor will not be able to start in any of the direction, not in the backward, not in the forward. So that's why a single phase induction motor is not a self-starting induction motor. This problem doesn't occur for a three-phase induction motor because we have seen in case of three-phase induction motor, every time we have seen, the rotating magnetic field is being produced because of the effect of all the three fluxes, and I used to have an equivalent field which is being rotating every time with a constant magnitude of 1.5 times the maximum flux. But this is not happening in case of single-phase induction motor. So what is happening in it is, at the very starting, the problem persists only at starting, At rest of the other cases, if you just see, I am getting the resultant. The resultant torque would be produced. If in any one of the direction, if at all I give an extra torque, the problem would be resolved. The motor will rotate in that particular direction, right? So the problem persists only at starting. So that's why this is the theory which is relevant to single phase induction motor and tells us why this single phase induction motor is not self-starting. Just now the torques what we have just discussed, that can be given by this torque speed characteristics. This is the torque which is being produced by the forward field by phi f, right? And this is the torque which is the lower one. This is the torque which is being produced by the backward field. At the very starting, when the speed is 0, the backward and the forward torques both are equal and or opposite. That's why the resultant torque is just 0 at the starting. Rest at any other condition, you may be seeing, at this instant the forward torque is greater, so I'll be having the resultant torque being produced like this, and in this case like this. So at any of the other situations, I'm having the resultant torque. So the problem persists only at starting. So we got the information that the single phase induction motor is not self-starting. Then how to get it started, right? Based upon the method by which we can start single phase induction motor, the single phase induction motor can be classified in its types, right? What are those types? If at all I just say, that is split phase induction motor. Second is capacitor start induction motor, capacitor start, capacitor run, and shaded pole. Quickly moving on to split phase induction motor, Now, the split phase induction motor, that very much the name itself says that the phase is being splitted, right? So, what is being done over here is, in addition to the main winding or the running winding, this is the main winding, this is the supply being given to the induction motor. This is squirrel cage induction motor. So, this is the rotor and this is the main winding, right? This is the main field winding of the induction motor. With this main winding or the running winding, a single phase induction motor stator carries another winding which is being called as auxiliary winding or starting winding. A centrifugal switch is also connected in series with that. This is a centrifugal switch which is being connected. The switch, that is, its aim is to disconnect the auxiliary winding from the main circuit when the motor attains a speed of near about 75 to 80% of the synchronous speed. Right? What used to happen in this is, earlier, if at all I just assume that I don't have any auxiliary winding or any starting winding in it, right? So, I'm having only main winding with it. If at all I just assume that way. So, in that case, if at all now I plot the phasor diagram, right? So, this is the supply voltage, Vt. So, where should be this I run, the current which is flowing in the main winding, right? As the nature of the main winding, it is highly inductive in nature, right? As this is highly inductive in nature, so the current would be lagging the voltage by a large amount, right? By a large angle. Fine, right? And we have also seen that this single phasor or the single winding is not sufficient to produce the required torque. Because of the double revolving field theory, I will not be having a resultant torque being produced in any of the direction. So, the motor is not going to get started. So, what we are going to do? So, now we are going to insert an extra winding in parallel to the main winding so that I am having a split of the phase. And the split of the phase would be occurring if the nature of this winding is different. And for that, this auxiliary winding what we are inserting over here, this should be a highly resistive winding. That's why the split phase induction motor is also being called as resistance split phase induction motor, right? So, in this case, this auxiliary winding used to be highly resistive. Now, in this case, if at all I just plot, this is Vt, supply voltage, running current, right? But now, I start, that is the current which is flowing in the auxiliary winding. This is highly resistive. So, in this case, this current will not be lagging the voltage by much of the angle, right? So, it will be almost in phase or would be lagging by small amount. Once again, I am having a nice split angle between the two phases, right? I used to call that as alpha, split angle between the two phases. Obviously, the amount of starting torque being produced is proportional to the slip angle between the two phases, right? So, now the resultant field would be occurring because of these two. Because of iron and I start, this would be my resultant field. The resultant field would be occurring over here. Resultant field or resultant current. As these two would be running, these are alternating, right? The resultant field will also be rotating, giving us an impact of rotating magnetic field, so that now the single phase induction motor will start. As the single phase induction motor will start and reach the speed near about 75 to 80% of the synchronous speed, the centrifugal switch will disconnect the auxiliary winding. I no longer require this auxiliary winding. I only require it to produce the starting torque, right? Now, the motor, once it starts to rotate in anti-clockwise direction or the clockwise direction, according to that, now, once the speed is being attained, it will be disconnected, the auxiliary winding would be disconnected from the circuit and only the purpose would be served by main winding, right? Now, considering the same pattern, right? The split phase induction motor, this is resistance split phase, it can also be splitted in case by using capacitor. Now just going with the applications, the split phase induction motor, this used to have a low starting torque and moderate starting torque, right? So these motors are used in fans and blowers, washing machine, pumps, lathe machines. And these motors are, generally having the ranges from 1/20th or 0.5 kilowatt of the range. Right. Another kind is capacitor start induction motor. Capacitor start, capacitor run, both would be discussed in the same. Now the same, in this case of capacitor start, what we are doing, once again we are splitting the phase. The main winding is once again over here. Now the auxiliary winding or the starting winding, that is being connected in series with the capacitor, which makes this auxiliary circuit highly capacitive. Right. This time it is not highly resistive, it is highly capacitive. So that if at all now I plot this phasor, the voltage is over here, IM, this is the main winding current, once again lagging the voltage because this is highly inductive in nature, right? And the starting current, this is highly capacitive in nature, it will be leading the voltage by certain angle, right? That is phi st being shown. So once again the split angle between the two, that has been increased if you just see compared to the earlier case. Right? As the split angle is now increased, then the starting torque produced given by the capacitor start induction motor would be comparatively much higher than the resistance split phase. That's why a capacitor start induction motor is much widely used. Right? Once again, I used to have the centrifugal switch. The function is the same. Once the motor starts rotating and it reaches near about 75 to 80% of its speed, the centrifugal switch will disengage this armature, the starting winding from the circuit so that the purpose is served only by the main winding. In case of capacitor start, capacitor run, in case of that, there will not be any centrifugal switch being connected to it, right? The capacitor would be permanently connected. In that case, the capacitor, if at all I say that is permanently connected, so what is going to happen with that? This will serve the two purposes. I don't require no centrifugal switch, right? Because the capacitor, it is providing me one more additional feature. What is that? If you just see, the resultant current over here is lying. The resultant current over here is lying here. And voltage is here. What is the power factor? The power factor is much more improved compared to the resistance split phase. So this capacitor start induction motor, they serves two purposes. Obviously, one is the starting for providing the starting torque, and also they provides a better power factor correction, right? If permanently connected. So obviously, for a capacitor start, capacitor run induction motor, the power factor is also very much improved. Now, so the applications of this capacitor start induction motor, these motors are having very high starting torque, and that used to be near about 300 to 400% of the rated torque, their operating torque. Hence, they are used in elevators, the grinders and air conditioners, compressors. They are available up to 6 kilowatts of the range. Coming to the last kind, that is shaded pole induction motor. Now, this is a different induction motor compared to this what we have just discussed. We have discussed till now the induction motor in which the phases has been splitted either by using the resistance or by using the capacitor, right? But here what is being done is the stator of the shaded pole induction motor has salient or the projected poles, right? So, what can be seen is the poles are projected outwards. So, these poles are shaded by a copper band or rings which are inductive in nature, right? So, this is, if this is the pole, it can be seen, a cut has been made and which this is being, a portion of the pole has been shaded with the help of a copper band, right? The poles are divided into two unequal halves. So, the smaller portion carries the copper band and is called the shaded portion, right? So, we know that the stator winding current is alternating in nature and so is the flux produced by the stator current. So we clearly understand the working of the shaded pole, right? I can consider 3 regions. What 3 regions, if at all I say this is the alternating flux, and I'm dividing it in 3 regions, 3 instants, right? This is the maximum value of the flux. This is instant 1, instant 2 and instant 3. At instant 1 or region 1, now the flux is changing its value from 0 to nearly positive maximum. In this rate, there is a faster rate of rising flux and the current is also very high. So according to the Faraday's law, what is going to happen? Whenever there is a change in the flux, the EMF is going to get induced. So with this positive rate of change of flux, what is going to happen is, I'll be going to have the EMF induced in the copper band as it is short circuited. So the current also starts to flow in this, right? Now this current in the copper band that produces its own flux, right? Now, according to the Lenz's law, the direction of the flux in the copper band is such that it opposites its own cause. And what is the very cause producing that flux? That is the positive rate of rise of current in the first region. The flux was increasing, the current was increasing, right? So the shaded ring, that the flux opposites the main flux, which leads to the crowding of the flux in the non-shaded part of the stator. And the flux weakens in the shaded part, right? If at all, I just see it. In case of first, if at all I say, in case of first region, this is the copper band which is being shaded, right? With the normal distribution of the flux, the magnetic axis lies exactly at the center, right? But now what is happening? If this is the main flux which is there, right? Now, this copper band, it will also be producing its own flux, right? Which will be opposing the rise in the flux. So this copper band is going to produce the flux in the direction which is opposite to the main flux, which is being shown with the blue lines. So in this region, both of the fluxes will cancel out each other, right? And so there will be a crowding of the flux towards the left hand side. So the magnetic axis will lie where? Towards the left hand side. Here will be the magnetic axis, right? If at all I go with the region 2, region 2 means when the region 2 was this, here at instant 2. There is neither the rise in the current, there is neither the fall in the current. So what will be happening to the EMF induced in the copper band? There is no rate of rise of current, the rate of change of current. So there will not be any induced EMF in case of instant 2. So at instant 2, what is going to happen? At instant 2, once again, if at all I just see the case, if this is the copper band, the main flux is downward and the flux produced, there is no flux produced by the copper band. The copper band, it is not producing any flux because there is no rate of change of flux. So I'll be having a normal distribution of flux. So the magnetic axis will lie exactly at the center, right? So the magnetic axis will lie exactly at the center here. So this is for the region 1, this is for the region 2. Now at the region 3, once again at the region 3, there is a rate of change of flux, but because of the decrease in the current, what is going to happen? In the third case, if at all I just see, this is once again a copper band, the normal distribution of the flux, right? Now this time the EMF induced or the flux produced by the copper band would be acting in such a direction to reduce the fall in the flux. So it will be producing the flux in the same direction as that of the main flux, right? Both the directions. So there will be a crowding of flux towards the copper band side. So the magnetic axis this time will shift towards which side? Right hand side. This is region 3. So it can be seen. Region 1, it was towards extreme left. Region 2, it has been shifted towards the center. And region 3, it has been shifted towards the right hand side. So there is a continuous shifting of the magnetic axis giving us a rotating magnetic field. Once the rotating magnetic field is there, we will be having the motor being started, right? But there is a disadvantage with this kind of shielded pole, that the power factor is very low, right? The starting torque is also very poor. The efficiency is very low. The copper losses are very high. We are using a copper band, you know. The speed reversal is also very difficult. It is expensive also. That's why it's found its applications to restricted applications due to its low starting torque and you know, the reasonable cost. These motors are being employed in small instruments, hair dryers, toys, you know, small fans, clocks. So these motors are usually available in the range of fractional range 1/300 watts and so. Thank you all. We'll be continuing on with rest of the topics.